Welcome, ladies and gentlemen, today's public talk. Just thank you so much for being with us today. We're here to celebrate 35 years of the Hubble Space Telescope. It was launched this month in 1990, and it observes ultraviolet, visible, and near-infrared light. And I have a feeling our speaker is probably going to share a little bit about Hubble's capabilities with you today. Hubble images planets in our solar system to galaxies billions of light years away. It has made way for JWST and the Nancy Grace Roman Space Telescope, which is called Roman. It's not an acronym, even though NASA loves its acronyms. Roman is for her name, Nancy Grace Roman, also known as the mother of Hubble, who was pivotal in establishing NASA's space-based astronomical observatories program for NASA back in the early 90s. So here today, we're going to have Dr. Emma Beasor, is currently a Royal Society Dorothy Hodgkin Fellow and academic staff member at the Astrophysics Research Institute, Liverpool John Moores University. She obtained her PhD from LJMU in 2019, and after which she was awarded a prestigious NASA Hubble Fellowship to continue her research at the National Optical Infrared Astronomy Research Laboratory, NORLAB, in Arizona. An expert on the lives and deaths of massive stars, her research focuses particularly on the behavior of stars leading up to supernovae, including how their stellar winds or nearby companions may alter their final fate. Please welcome our speaker, Dr. Beasor.
Okay, hello everyone. I'm really pleased to see so many of you here today. I'm going to be talking about how the Hubble Space Telescope has helped my field in particular, which is massive stars and supernovae. So it's been 35 years of Hubble this year, which is amazing because initially when Hubble went up, it was expected to only have a lifetime of around 15 years. But it's still going strong 35 years later, and it's still one of the most hard to access telescopes in the world because everyone wants to get time on it every single year. But it all came about after this first paper where Dr. Lyman Spitzer first wrote a paper in 1946 talking about the advantages of putting a telescope in space rather than observing from Earth. So this was the first paper that ever kind of posited the idea of the benefits of having a telescope in space. And this image in the left is kind of an artist's concept of what that might look like. So that's from the 40s. So the question is, why put a telescope in space? There are a lot of advantages to doing this. The first is you don't get affected by things like light pollution so much. So I'm from a city, so I didn't see many stars growing up. And you'll notice when you go to quieter areas or areas out of the city, you'll see more stars. And that's just simply because the lights from houses, cars, lampposts, everything like this, they kind of cause the stars to kind of fade out. It's harder to see them. So if you go somewhere with a truly dark sky, so a rural sky, you can start to see it, but with a truly dark sky, you can get a really, really clear image of the Milky Way just with your eyes. And that's something that you'll never see in central London, for example. So I used to live in Tucson, and that is actually a dedicated dark sky zone. So it's pretty dark there, but it's still not as good as putting a telescope in space, because if you put the telescope in space, you don't even need to worry about city lights or anything like this. You completely avoid this whole issue. Another issue with having telescopes on the ground is that we have Earth's atmosphere in the way. And Earth's atmosphere is great because it protects us from the sun, but it also puts this big layer of turbulence, material, of absorbing layers between our eyes and the sky. So you can get a much clearer image if you put a telescope out in space because you aren't looking through the atmosphere. So on the left, there is an image of Pluto and its little moon. From a ground-based image. And you can see that when you look at it with HST, you get a much clearer idea of what is going on with Pluto and its moon. And then on the right, there is a galaxy, spiral galaxy, and you can see in the ground-based image, it looks pretty blurry. You can't make out any features. But as soon as you look with Hubble, you get a much clearer idea of what is going on. you can see that the object on the left is not just some blob or some star. It looks actually more like a galaxy. It's got spiral arms. And this kind of thing is really difficult to do from the ground. It is possible to get clear, sharp images from the ground, but it takes a lot more work. Whereas if you have a telescope in space, you don't need to worry about the atmosphere at all, and you just get very high resolution images. Another reason is that having a telescope in space, this is just another image showing how sharp things can be. So you can see the difference here between the image on the left and the image on the right. You can make out all of these far more detailed objects. So they now look like proper galaxies surrounding this much larger galaxy. But having the telescope in space also gives us access to wavelengths that are difficult to see from the ground. And that's because the atmosphere absorbs certain wavelengths of light. So there are huge absorption features when you observe from the ground that you have to kind of like balance out by taking extra observations to kind of subtract them from the image. It's a lot more complicated. But if you look from space, you get a much clearer image across multiple wavelengths without having to worry about any interference from Earth's atmosphere. So you have all of this access to these wavelengths that are just not attainable from the ground. For example, the ultraviolet is particularly difficult from the ground because we don't want too much ultraviolet to reach us. We have the atmosphere protecting us for that. But for astronomical observations, the UV is super useful because it shows you all of this hot material and you can really get an idea of what's going on. For example, in an object like this, which is a supernova remnant, you get a much better idea of what is going on when you look across multiple wavelengths of light. So different wavelengths trace different things in the system. So kind of hotter material will be traced better by ultraviolet, X-ray light, and then kind of cooler material like your dust will be traced better by radio and infrared light. But for optical, ultraviolet, and infrared, which is where Hubble sits, it's much easier to get clear observations from space. So those are the main reasons for putting a telescope in space. Obviously, it's expensive to put them up there, but astronomically, it is worth it. So it was launched in 1990, April 24th. So this just shows Hubble going up on NASA Discovery, so the shuttle there, and being launched into space. It took a few days, and it sits in a low Earth orbit, so it's a few hundred miles above the surface of the Earth, and that's a good spot because it's actually serviceable from the Earth. So we used to have the NASA Discovery shuttle would go up and would allow astronauts to go and modify HST, would allow people to improve it or change instruments out. It was really easy to do servicing upgrades to the telescope from the position where it was. And that's a good thing too, because after Hubble went up, the first images weren't super impressive. So the image on the left is the first light image that came out of Hubble. And there was actually an issue with the shaping of the mirror. It was a little bit off. So the light, instead of focusing on the one single focal point, kind of focused all over the place. And you ended up with these super blurry images. But luckily, we could send up some astronauts to go and correct this. They basically put a lens in front of the mirror. And that meant that we could get the sharper images that we see today. And there have been a lot of servicing missions up to Hubble. So there have been 6 successful ones. So 5 successful servicing missions, sorry. And they've done things like upgrade instruments, change sensors, do all kinds of work. So there's been 5 upgrades, and then that all went on until the Discovery shuttle was retired in 2010 or whatever year that was. So since then, we haven't been able to upgrade it, but Hubble's already vastly outlived its predicted lifespan. It was only meant to be up 15 years, but thanks to these servicing missions, it's already lasted 35 years and seems to still be going pretty strong. So just a few facts and figures about Hubble. It has taken like 1.7 million observations to date, and that's over 100 million objects which have had data taken. But this is actually only 0.1% of the sky. So even though it looks like it's taken a lot, the sky is really, really big, and it's very difficult to image huge areas of the sky. And then the most furthest object that has been observed was a galaxy at 13.4 billion light years away. So that is a really high redshift galaxy right at the dawn of time. But now I'm going to talk about more what Hubble has showed us in my field, massive stars and supernovae. And I'm going to begin by going over some basics of what is a star. So a star is a hot ball of gas. It'll spend most of its time fusing hydrogen into helium. The most famous example is our sun. But I look at massive stars. So massive stars are around 8 times the mass of our sun, at least. They can be much bigger, but at least 8 times is generally the cutoff, what we consider to be a massive star. And these objects are much rarer. They have vastly shorter lifetimes. So only around 1% of the stars you see in the sky are massive. So they live short, fast lives. And when I say fast, I mean astronomically fast, as in a few million years. But to me, that's pretty quick. And so these stars don't live the same way our sun does. They have, well, in my opinion, far more interesting and dramatic lives than a star like our sun. So we'll start off with how are these stars born? So the first phase of massive star evolution is they all form from a star-forming nebula. And the Orion Nebula is, the Orion constellation is actually a really great example, a really great object to point to when talking about the lives of massive stars, because we kind of have everything going on here, every phase of a massive star's life. So there's some massive stars in the belt, some blue supergiants. We also have Betelgeuse up on the shoulder of Orion. So that is a red supergiant. So I'll come on to that in a little bit. But then down here in Orion's sword, we have this little smudgy area, kind of looks pinkish on this image. And if we zoom in on that, that is actually the Orion Nebula. So there's a lot of dust and gas here. And this is one of the nearest massive star forming regions. So you can think of it as like a stellar nursery. So this cloud doesn't just sit, it looks beautiful, but this is where massive stars are born. So here is another image of the Orion Nebula taken with Hubble. This is taken across multiple wavelengths. So you can see again that when you have multiple wavelengths, you can really pick out a lot more detail in these objects. You can see what is going on far better than when you just have, for example, just optical or just infrared. And another way of showing that, so this is another Hubble set of Hubble images. So this is the Lagoon Nebula. See if this will play. So this is the image in kind of visual light. You can see there's big dusty plumes. It's really difficult to see what's going on. But when you swap to infrared, as the video is doing now, you can start to see through the dust layers and you can see all of the stars that are forming behind the dusty plumes that are in the way. And this is something that you need multiple wavelengths to see. But these clouds of gas don't just sit there. They have their own gravity. And so this gravity forces these clouds to collapse. And as they collapse, gravity will cling to gravity will force massive lumps to cling to each other. So you'll end up with this kind of knotty structure, collapsing cloud material buildup around knots. And as the cloud collapses, this increases pressure and increases temperature, and eventually you will get a protostar. So this is a simulation of what it's like when a star collapses. So this is just a cloud. This is at 0 years. Then over the next few million years, you can see that the material is collapsing, and you can see it kind of forms these filamenty type structures. And you can see little circles lighting up. That's where stars are beginning to form. So I think it's thrown off energy and stuff. I don't think those are stars, but you can see that the more yellow areas are areas of higher density. So you can see that as these clouds collapse, they start to form all these structures, and in these dense regions is where we can get stars forming. So the next phase of a star's life is it will become a protostar. So it's not quite burning hydrogen in its core yet. It's just starting to warm up. So we're on our way to forming a star, but we're not technically there yet. And this is an image not from Hubble of a protostar. So this is kind of what they look like in real data. They're kind of just very dusty, very smudgy, and they have these jets where they're throwing off energy as the protostar is spinning. And this is, the smudgy bit in the middle is the star, and then we've got the jets indicated by the arrows. So these regions are super dusty, and what that means is it's really difficult to see what's going on, but also not all of this dust will go into the star. It will go into the interstellar medium. Some of it will be forming planets, some of it will be forming asteroids, but as I said, the dust really obscures our view. But at some point, these protostars do get hot enough that they start burning hydrogen in their cores, and we finally have a star. And depending on the mass of the clump, this process can take different amounts of time. So for a star like our sun, the amount of time it takes for that cloud to collapse is probably about 50 million years. For a massive star, it's probably just a handful of a few million years, maybe 5 million years or so, which is a flash in the pan compared to a lot of astronomical events. So then we eventually have a star, and now we move on to the main sequence of evolution. So the main sequence, so this figure just shows basically how astronomers divide up stars, how we categorize stars. So we basically put anything we see on a plot of temperature versus brightness. And this is just how we group stars together. So the type of stars that I'm looking at mostly are red supergiants. So they're really, really bright and they're really cool. So they're all the way over here. So this goes opposite to the way you might expect. We have cool stars over on the right. But most stars will spend their time, the majority of their lives, all stars will spend the majority of their lives on the main sequence. And this is where they're burning hydrogen. So they have a good amount of fuel in their core. So our sun is here at the minute, and it's a one solar mass star, and it's about 5 billion years old. And it's probably about halfway through its life. So it's got ages to go. But a star more massive than that, so around an 8 solar mass star, will probably only live on the main sequence, like at most 20 million years. If that, probably more commonly around like 10 million years. So massive stars, again, a vastly shorter life, orders of magnitude shorter. But these objects, to spot a star in the main sequence, they're hard to see because they're around all this dust. When a new cluster has formed, there's obviously all this material still around it from these star-forming nebulae. So you have to wait for winds to kind of kick in these stars. And at this point, the winds will blast out all of this dust out of the way, and you can start to see what is going on. So you have to wait a bit, but eventually the stars have winds, and this is another simulation of what's going on in a cluster. And the winds start to clear out all of the dust that's in your way so that you can't see when you're looking through the visual bands and what you can see with your eyes. Start to clear all the dust out. And this is just basically a collection of all the stars in the cluster, all have winds. Eventually supernovae start going off, but I'll come on to them in a bit. And it clears all of the dust out of the way. One star that is very good at this is a star called a Wolf-Rayet star. So these are massive stars with really, really strong winds. So winds can be as strong as fast as 90,000 miles per hour. And if you have a lot of these objects together, you can imagine that's going to get a lot of dust moving. And so this is a Hubble image of WR124. So that's the star in the middle, and then these are kind of like the dusty outflows from it pushing all of that material out of the way. And eventually, if you have enough stars doing this, you can begin to see through the dust into a cluster. So if we look here, so here are some more lovely Hubble images of star-forming regions. So the image on the left is a cluster within the giant nebula. So that kind of red gas stuff is kind of indicates star-forming regions. It's called a H2 region. There's dust in there. There's material in there that is like the fuel for stars. But you can see that there's been enough star formation and enough winds going on that they've kind of cleared a little bubble out in the middle of this nebula. And the same thing is going on in the Eagle Nebula with the pillars of creation. You can see that, it's not completely covered. You can see there are regions where you can see through the dust and you can see more stars. And that is because these young star clusters have started to blast away all of this material. So that's the kind of process that gives us these really dramatic looking dust plumes. And you can see that Hubble can pick up a lot of structure in these objects in a way that just from the ground we just can't really do. So looking for these young clusters is really important because there are a lot of massive stars in them. And as I told you, massive stars are rare. So we need to be looking in clusters to find them. And the easiest way to spot them is to look at other galaxies. So this is M83. It's otherwise known as the Southern Pinwheel Galaxy. So if we zoom in here, so this is looking still a HST image, but now looking more at the infrared. So all of the red points in here, all of the kind of blobs like that, those are all superstar clusters. So each superstar cluster contains around 1,000 times the mass of our sun, to around 100,000 times the mass of our sun. So they're far bigger than our sun, and they contain a lot of mass in quite a compact area. And so we like to look for these in external galaxies. And the reason is that a lot of star clusters lie kind of in the plane of the Milky Way, which also happens to be where we are. So it's like if you're trying to tell the pattern of like a china plate by looking at it from the side, it's going to be really difficult to see. But it's also really difficult to look into the plane of the Milky Way because there is so much dust there, and dust has a major impact on observations. So just kind of show that like this. So when you look at a normal main sequence star without any dust in the way, it might look yellow, and you see it as yellow because there's nothing in the way, so you just see the star as it is. But if you stick a cloud of dust in the way, all of a sudden the dust starts to scatter the light that's coming from that star, and it starts to re-emit it at longer, redder wavelengths. So when you start to look at this star now, even though it's the same star, it will look dramatically redder. So you're kind of shifting what you can see to the kind of cooler region of the spectrum, to the kind of redder region. And you can see this when you look at clusters. So this is a cluster on the left. This is one that's not in the plane of the Milky Way. It's not very dusty. So you can see all of the stars look kind of blue in that image in particular. And then Westerlund 1 is a different cluster, but this one is obscured by a lot of dust. And you can see that it just kind of has a red haze over it. Everything looks much more red. So the image is kind of obscured. It's really difficult to take this into account when it's in the Milky Way because the dust amounts can be quite dramatic. Westerlund 1 is a particularly difficult cluster to observe. And it's, not just changing the color. Sometimes this dust can be so dense that it can, well, not dense, but it can block out so much dust that you can't really see anything at all. So if there is loads of dust, you might not even know there is a star there until you're looking in the right wavelengths. So in the Milky Way, you can see this when you look at these kind of dust lanes. They just look like there's no stars there at all, but in reality there are. It's just the dust there is blocking all of the light that's coming out from the stars behind it. So if you looked at this in the far infrared, you'd probably be able to see through it and see all of the stars. So we look for superstar clusters to identify stars on the main sequence, mostly in external galaxies for this reason. And once a star has gone through the main sequence, it will finish burning hydrogen and it will become a red supergiant. So these are the kind of stars that I work on primarily. So I will tell you a little bit more about those. So this is our sun type star next to a red giant star. So for our sun, it will finish burning hydrogen, and it will start burning helium, and it will swell up a little bit. So this is kind of the objects to scale. So you can see the sun. Let's see if I can get the mouse over here. You can see the sun here compared to a red giant. So it does look like a dot. So it's about 200 Earth radii, that little scale bar there. So it does swell up. So that's because the hydrogen burning releases more energy, and the star will expand and cool. So yes, you run out of you run out of hydrogen in the core and you move on to helium burning, so the star will begin to expand. And that's kind of to scale a red giant, but the type of stars I look at are red supergiants. So they're even more expanded than a red giant star. So to scale, kind of looks like this. So the sun is basically just a little dot, and these can be thousands of solar radii. So they're very, very expanded, very, very bright, and very cool. So here's another image just showing kind of to scale. So VY Canis Majoris is a famous red supergiant in the Milky Way. And you can see there that the sun, again, is just a little dot. You can't even see it in the big image. And then that circle there just shows the radius of Earth's orbit. So it really is very dramatically bigger, very dramatically big compared to even a red giant, which are very big compared to the sun. So if we put this in the scale of our solar system, a red supergiant would actually reach the orbit outside of Saturn. So they're really, really huge. So this isn't to scale again, but red supergiants are hugely vast in radius. But the surfaces of stars don't actually look all smooth and nice like you see in images. So this image shows the convective cells of the sun. So when you zoom in on the sun, it actually looks super granulated. There's lots of little cells here, pockets of energy. You can see there's lots of changes in temperature over the surface of the sun. It's kind of lots of material is kind of churning itself up. It's all convective. It's like you're boiling a kettle. And surfaces of red supergiants are kind of like this, but on a much bigger scale. So this is a simulation of a red supergiant, and you can see that these convective cells can take up sometimes half the radius, half the diameter of the star, half the radius of the star. So they can be huge convective cells pushing all of this energy around. So if we could see a red supergiant up close, maybe that's what it would look like. But in reality, what we tend to see when we look at red supergiants is something more like this. So this is VY Canis Majoris, that red supergiant that I mentioned before. And this is it imaged with Hubble again. And the star is in there, but it's surrounded by a lot of dust. So that's because these stars lose a lot of material. So all of these convective cells drive winds, and the dust around the star condenses, and you end up with this really non-circular, non-symmetrical object. It's not even really what you would expect when you think of a star. It just looks like a mound of dust, but that is what the star actually looks like. And so our nearest red supergiant is Betelgeuse, as I said. So that's up in the shoulder of Orion. So it's kind of less dramatic than VYCMA. VYCMA is a particularly dramatic red supergiant. It has crazy high mass loss rate and it looks really dusty. Betelgeuse is a little more normal, so it's a little more relaxed than that one. It doesn't have these crazy outflows like VYCMA, but it is an interesting red supergiant because it's so close and we can study it so much easier than a lot of other ones. But after the red supergiant phase, we move on to a much more unstable phase of evolution. So the red supergiant phase might only last 1 million years. But towards the end of that, you get into this really kind of difficult to access territory because each phase gets shorter and shorter as you approach supernova. So we approach this phase where stars can have very explosive, very dramatic outbursts. So one such system is Eta Carina. So that is this object here, again, imaged by Hubble. So this is an extreme object. So this is a luminous blue variable that had a great eruption in the 1840s. So it became one of the brightest objects in the night sky. So people could just see it just looking up. It ejected 10 solar masses of material in one single day. And it did it in a very non-uniform way. So it's all very asymmetric. You can see these huge they're called the homunculi, but they're just these huge kind of blobs, and you can see all the material around it. It's still growing to this day, so we can still track this object. So when you look at it with data now, you can see you can see the dust and the material continue to move. So again, this is Hubble imaging. So you can track the outflow and you can track the evolution of this one object just by going back and imaging it with Hubble, and you can see how fast things are moving. It's a really interesting object, actually, because it probably wasn't even just a single star. It was likely an interaction of two stars in a triple system. So it's all very complicated, but that's probably what led to this kind of crazy outflow. But a lot of massive stars have really peculiar, really difficult to understand outbursts in their final phases. This is one that's very easy to see that it's weird because it's so close. Usually we don't get this kind of level of detail. So after this, as I said, each phase up to the star exploding gets shorter and shorter. So for a while in the core, you're burning hydrogen to helium. That takes about 10 million years. You're then burning helium to carbon. That takes about 700,000 years. Oxygen to silicon might only take about 6 months. So we're getting much, much quicker. When you're fusing silicon to iron, that might only take a day. So at some point, all of the core is fusing to heavier and heavier and heavier elements, and you end up fusing silicon into iron. And iron is, fusing iron is an endothermic reaction, so it absorbs more energy than it puts out. So what that means is the power source of the star has just basically switched off. And so we end up with a supernova. So this is kind of a schematic showing what is going on. So for most of the star's life, you've had energy being output from the core, from the fusing of hydrogen to helium, helium to carbon, et cetera, et cetera. But now all of a sudden you've got an iron core, so there's no energy being put out. So there's nothing stopping the star collapsing against its own gravity. You've just completely switched off this outward force. And so gravity takes over and becomes the dominant force in the star's life. And the outer layers of the star now come crashing down onto the core. And this is what ends up with a supernova, but I will show you a better simulation than that. So this is just an artist's impression from NASA showing what's going on when a star goes supernova. So an observer will see a very bright flash as the light escapes from the dying star. And the star has lived for a few million years, but this process only takes a few seconds. So the outer layers will crash down onto the core of the star at a quarter of the speed of light, and the shock bounces off the core, and you end up with this very dramatic supernovae. And then years later, you end up with a supernova remnant, and I'm going to show you some great images of those in a minute. So this is an artist's impression. But we've been observing supernova for a long time, since way before Hubble, way before telescopes. So this is some drawings that were found in Kashmir, India from around 4000 BC. And you can see there are some stars, two suns in the sky. And it's been suggested that maybe this was a supernova that went off. So potentially. There was also another historic supernovae observed in 1054, which Chinese astronomers kept very good records of. They called it a guest star at the time. And they said it was so bright that you could see this object in the day. So on the left, it's showing what that supernova may have looked like to people observing, to these Chinese astronomers on the ground. So you can see it would have really stood out compared to other stars in the sky. And what it looks like today is this. So supernova 1054 today now looks like this. So this is the Crab Nebula. This is what is left over after a supernovae. So it's expelled all its outer layers, and you can see a lot of structure, and you can see a lot of where the shock front has come. You can kind of see that something has exploded, and it's just kept expanding since the supernova. So this is a really cool object. So this is a Hubble image again. You can take measurements of these kind of outflow regions of the dust you can see, and you can kind of trace it back and pinpoint exactly when the star exploded and what directions it may have exploded. And you can tell which bits of material are moving faster than other bits. And you can say a lot of stuff about how supernova work. when you look at supernova remnants like this. So a more recent supernova that went off, which unfortunately was just before Hubble, was supernova 1987A. So this was the first supernova that we'd observed go off in the Large Magellanic Cloud, which is one of our nearest satellite galaxies. So you can see when the supernova goes off, the light really dominates the galaxy. You can see it's really bright. It would have been super exciting to see that and take images of that. But this was one of the first supernovae where we had prior imaging of the galaxy before the supernova went off. So we can figure out the star that exploded. Today, 1987A looks like this. So it's in there. And again, it's a supernova remnant, but it's got a completely different structure to that one I just showed you, the Crab Nebula. So this one has kind of like a double ring structure. And a lot of people are trying to work on like why this system has a double ring. A lot of people have spent their entire careers just looking at this one single object because it's near enough that we can get a crazy amount of data on it. We get a really good idea of what is going on with the remnant, how it's structured, and we've been able to see it change since 1987. So the double ring structure, most people think that this is caused because it was actually a binary system that maybe collided and exploded. So every time we detect supernovae, we put them into categories, and every time we can't fit them in a category, we just say it's a peculiar supernova, and this is one of the peculiar supernova, one of many. So it doesn't quite fit into any of the categories that we have, but so we just tend to call things 87A like, or make a whole new category for them. And again, just showing that if you see these supernova remnants in different wavelengths, you can trace different features of the object. So this is the Ring Nebula, I think. So you can see with the Hubble imaging here, you can see like a green ring. So that's kind of hot material, that's kind of the shock front, oxygen as well. And when you look with radios, like millimeter data from ALMA, you can see a lot of red, so it's really cool, dusty material. And then when you look in the X-rays, you can see even hotter materials. So all these, this blue ring here is extremely hot material around the supernova, around the remnant, sorry. And again, here is the Crab Nebula across multiple wavelengths. So I showed this before, but I just think it's really cool that, people think that when you look at an object, you're going to see it like this, but actually it's a layered object with a lot of different information in it. And just looking at this, astronomers can tell you all sorts of information just based off where these colors are dominant, and we can tell a lot from this. So, and then we combine them and we get these really striking images. Okay. But generally, supernovae we see aren't that near, so we tend to see them in galaxies that are further away. So I'm going to show you a supernova that's going off in M51, and you can tell me if you can spot it. Can people see it? No? Let's show you again. Okay. Yeah. So luckily we generally have computer programs to search for these supernovae for us, but some people are very good at identifying supernova. There are actually a lot of amateur astronomers who will find supernovae before we do. But yeah, this is a supernova that went off in M51. And generally that's the kind of data we get. So you can see that the light really dominates that region of the galaxy, whereas before, there was absolutely nothing of note there. And there's the supernova. But the nice thing about Hubble is it's been up imaging galaxies for so long now that there is a lot of data from before stars go off that we can use to go back and identify a progenitor star. So in this case, the 2017 image shows a supernova. If you squint very closely in the 2007 image, you can see a progenitor star. So we can actually directly link supernovae to their progenitors. And this is not Hubble data on the left and right, but it's a nice example. So the middle image shows a supernova. And then in the pre-explosion image on the left, you can identify a red star. And then if you're very patient, you can wait for the supernova to fade away and you can go back and you can see that that star has now gone. So we can learn a lot from this. Firstly, we can say that is the star that exploded. And then we can go back to the early data and we can figure out how hot the star was, how bright it was. Was it a single star? What was it doing before it exploded? And we can really pull a lot of information out from this. So Hubble's been amazing for this, for allowing us to directly link supernovae to their progenitors. So Betelgeuse, as I said, is our nearest red supergiant. So how bright would that look? Well, someone at UCSB calculated that if Betelgeuse exploded tomorrow, it would look as bright as a full moon in the sky. And it would stay like that for a few hundred days. So that's pretty cool. But we can also learn about supernovae from Hubble after the supernovae has seemed to fade, and that's using something called light echoes. So we're just zooming in on the site of a supernova now, and these work the same way that echoes in a room work. So, our voices bounce off walls and we can hear them play back to us. And you can see here that the light is echoing as it moves through material. So you can spot light echoes as the shock of the supernova actually hits different material. And we can use these echoes again to say something about the supernova. We can trace them back and we can figure out how fast is the ejector moving, how was it interacting with the material at each different point. So it's super cool. So this is, again, Hubble imaging following light echoes of supernova. And yeah, so these supernovae are hugely important. They are furnaces for fusing heavy elements together. So this is just the periodic table. And everything with a green box on it is all of these. These are all elements that can only come from the deaths of massive stars in the quantities that we see them. So they're fusing a lot of heavy elements together. You see oxygen, iron, neon, aluminium, so these supernovae are making the gold that we see, all these heavy elements. They make all of the calcium in our bones, and they make everything that you need to make a dog. So supernovae are the most important, one of the most important processes going on in space. And this supposedly completes the cycle because now these stars have pushed out all of these heavy elements into the ISM, and you'll form a new nebulae, and you can go on forming planets, stars, everything. And that has been the picture up until very recently. So I'm just going to very quickly show you new information that we're getting about how these massive stars may live. Okay. So another option is that maybe not all these massive stars are exploding after all. So telescopes are scanning the sky looking for things that get brighter. But sometimes you can look for things that get fainter. So this is a red supergiant, so I've circled it in the middle. And this is a Hubble image from 2007. And when you go back in 2015, oh no, that's gone off. Hang on. It's okay, it's opening back up now. Yeah, I'm still connected, but I can't get the PowerPoint up now.
Pardon us. Stop sharing. And you've got your PowerPoint here. Where is it? I don't know. It's probably hiding behind here. Oh, let's do that again. Like that.
Can't see it.
Yeah,
It
you're right.
crashed.
Did you put
I put it on the desktop, so it's not, yeah.
Where are you? Right here?
Yep.
Make sure that's on. Oh, there you are. I saw you. Where'd it go?
Maybe quit it and do it again.
Yeah. I will. Let me try sharing it. See if it shows up when I share it.
Oh, I see it.
Oh, it is there. It's right here. 1 second.
Just get over there.
Yeah. Which slide do you want me to be on?
Oh, it's way down.
Maybe keep going?
Yep.
You do have a lot of stuff.
I do have a lot.
Great, great.
Okay, so it is. Yeah, okay.
90.
Maybe no, 18 minutes, sorry.
Yeah.
Yep.
Can we just make sure we're sharing? Should be.
I don't know if that'll work now.
We'll see. It does look a little different, doesn't it?
Yeah.
Like sharing that one. Yeah, we're sharing. We need to share this one. Weird. Looks okay. Wanna try it? I'll go check this.
Yeah. Click it, I think, and see if it works. It should fade. Oh,
It closed again.
no. I know.
So it's already quit, so I think it's just gonna be a buggy image again.
Okay.
Sorry about that.
Can I go on Google and look it up?
Yeah, go for it.
Okay. Go on there.
Go for it. Try that now. I'll move it over once you find it. I'm trying to make it work, everyone. Sorry about you have to wait here. She really wants to show this to you, which I think is great.
Okay.
We move that over.
Okay, so just pretend that one image faded into the other. But this star just completely disappeared in the Hubble wavelengths. When you look back with Hubble in 2015, you can't see anything. And so right now I need to go back to the PowerPoint. And so that started everyone wondering, how do I get back on the PowerPoint now? That's it.
Be on 91, so it doesn't
All right.
go back down. Let's see if we can go here. Choose. Oh, that's not gonna do it either. It's way too big. 91,
Okay.
91.
91 now, yeah. 90 or 91. Yeah.
So we don't get the bug.
Yeah, good. Yeah.
Let me just make this bigger.
I think this one's a skip slide. All right, it's there. Cool. Oh, jeez.
It just quite.
It did, yeah.
It looks like that's the buggy one.
Right. Sorry, everyone.
So it's closed.
Is it closed completely?
Yeah, it closed completely. Yeah, that's it. There we go.
Go back and delete that slide.
Okay, it's over here on the a bit tricky.
Okay. It didn't even go then.
It's gone completely.
It's gone completely. Okay, right. I'll
You
delete
might
these
have,
slides.
what you might have to do, which I would suggest, is it will still show on PowerPoint. I would say don't go into presentation mode,
Okay.
because it seemed to be okay if it just stayed out of presentation mode for now. So let's try that again. Is that the right one? We'll fix it later. Sorry,
Yeah,
everyone.
no.
So I would say just stay here.
Okay.
And I can make this bigger in a second. Hopefully. Go to 91 or 99?
90.
Still there.
Okay.
Mm.
So we can just leave it there.
Yeah. Just make this a bit bigger. Okay, that's gonna have to,
Okay.
you'll have to use the cursor over here to
Okay,
get the
cool.
next slide though, okay?
Okay. Oh dear. Okay, so that was an otherwise normal looking red supergiant, so a star that we would expect to die as a supernova, just kind of blinking out of existence. And it was suggested that maybe these kind of stars, rather than explode, are just collapsing directly to form black holes with little or no visible explosion. And And so this has been something that has been suggested by theorists. I'm just going to skip that slide. And it would kind of explain, because with LIGO, Virgo, these gravitational wave detectors, we are detecting a lot of lower mass black holes. We are detecting a lot of things that maybe we didn't expect to see. So some people think that maybe this is a missing piece of stellar evolution, that these stars don't explode, they just collapse. But another option is, I showed you before, how dust can affect what we see. Another option is that this kind of disappearing star is actually just a hugely dusty red supergiant hiding behind its own material. So maybe it had some kind of crazy outburst, or maybe it interacted with another star. And the only way to kind of see that is by looking at redder wavelengths. And unfortunately, we can't do that with Hubble. So the only way to do that is to look forward with JWST. And so we were lucky enough to get data of this a couple of cycles ago. I can't see what I'm doing. So we got JWST data of the site of that disappearing star, and you can see that when you look in the infrared, there is still a bright source remaining across multiple wavebands. So it is overall fainter than what it was in the Hubble images, but there is still a source. So we're still trying to figure out what is going on with this object, and we are getting more data in probably in a year or so, hopefully sooner. And we're trying to figure out what could have happened to this star that caused it to look as if it disappeared. But JWST and Hubble kind of need each other. They both complement each other. So while some people have been wondering, is James Webb a replacement for Hubble? It's not at all. It hits a completely different wavelength range, and we see completely different things with James Webb. So we're all still hoping that Hubble keeps going for many more years. So just some stats from astronomers. So every year there are around 1,000 or so proposals written for Hubble every year. And the chance of having a proposal accepted is only around 1 in 5. That's how oversubscribed it is to get time on Hubble. There's been over 21,000 peer-reviewed papers using data from Hubble, and each paper, together these papers have all been cited over 1 million times. And 25,000 professional astronomers have used Hubble, which is surprising because I didn't know there was that many astronomers, but apparently there are. So we're all hoping that we get a few more years out of Hubble, and we're very grateful for having 35 years so far, but it should keep going. So thank you very much for listening.
Thank you so much. That was fantastic. And we have a few minutes for questions, and Pam is going to host that.
I hope this is not too silly a question, but in terms of Wolf-Rayet stars, is there any chance that one day, at the end of their lives, they become a hypernova?
They probably become stripped type supernovae, so it would depend on the mass. I think hypernovae, I mean, and it's probably more energetic than a Wolf-Rayet could produce. Yeah.
If Betelgeuse or similar red giant was to go supernova, what would be the area or diameter of destruction?
Oh, it wouldn't get us, so you don't need to worry about that.
Yeah.
I don't know in terms of, I mean, they move pretty fast, but it's kind of isolated, so it's not going to hit anything else for a while.
Okay, how many light years would it stretch out to? If no,
It's a good question. I'm actually not sure.
Right.
Yeah. Eventually, like, I mean, some of these remnants, stretch out quite far. But I mean, if you look at 87A, it's only a few parsecs. It's not super big yet, but eventually they keep expanding, right?
Okay.
Yeah.
Good.
Yes, could you actually tell me at the beginning you mentioned about the fact that these telescopes are out of the limits of the Earth. There's a telescope called the Very Big Telescope.
Very large telescope.
Very large telescope. Now, why have we got that then?
So the VLT is still a hugely powerful instrument. So it's got a much bigger collecting area than than Hubble, and it has different instruments, different wavelength capabilities. The advantage of the VLT as well is there's a couple of them, and you can use it to get really precise measurements when you like kind of like team them up, or like a very long baseline. And it's great putting stuff in space, but it's really expensive and hard to maintain. Whereas a telescope like the VLT, you can add new instruments to it all the time, and they're always doing that. And you can just go and polish the mirrors when you need to, and do all of this. But it hits different wavelengths to Hubble and has a different collecting area, all things like this. Yeah.
Lucinda has a couple of questions from online to read for us.
Yes, from our Zoom audience, Julian asks, are we any nearer to being able to predict when a supernova will happen?
People are trying to predict when Betelgeuse will explode, for example. So it kind of had this phase where it kind of like dimmed a little bit a few years ago, and everyone thought that, oh, maybe it's gonna go, but at the minute it's too hard to tell. And there are people who are looking for, it's called precursor emissions. So before a supernova goes off, they might have little outbursts or little dimming episodes, and there are some surveys that are trying to catch this, but it happens on such a short time scale that it's really difficult to observe. So hopefully we'll figure that out and spot them early, but yeah.
That was definitely the second question. So I want to know any updates on the research on Betelgeuse and when that will, but you mentioned that.
Yeah.
How quickly will a supernova, and we might not know this, become clear to us on Earth? Will it be seconds or gradually become more and more visible as a supernova over some time?
I mean, it depends where it goes off. The further away, the longer it'll take for the light to reach us. So it depends on the galaxy.
And someone did ask to know, I think you probably mentioned it in your talk, but maybe we can remind us that what would be the typical mass of a red supergiant?
They're between like 8 and 30 solar masses.
Thank you.
Any more questions? Thank you, and thank you very much for your. Do you hear me?
Yeah.
Okay, and thank you for your presentation. I just wanted to know when there is gases in front of a stars, how bothering is it? Meaning, at the point of is it really something which is like, oh, it's behind that, and so we can't look at it, or you know what the cloud is made of, and so you can predict what is behind, and can you see behind God's spectroscopy, and how do you get behind the cloud?
Yeah, so if you look at different wavelengths, you can start to see behind the cloud. So you can tell what is there. The main issue is when it comes to figuring out how like bright the star is across all wavelengths. So to know how its total light output. If there's loads of dust in the way, then it looks really faint in like the visual light. So you kind of have to figure out how much dust is there, and you can do that by looking at a star where you know what it looks like, and then you kind of figure out, well, there's this much dust in it to make it look like this, and then you kind of have to apply these corrections to what you're interested in. So it's tricky and it's fiddly, but you can do it.
More questions coming online from Lucinda.
Another question came up. They want to know, how do we know what happened in this area of the sky where our sun is? I understand it was born from solar nebula. However, there's the idea of it being born from the collision of Sagittarius galaxy with Milky Way galaxy.
I don't know anything about the sun's formation, I'm afraid, but it will have formed in a nebula. Whether or not that is from, things colliding at some point before that, maybe.
Thank you. And do you supernovae ever take out other stars in the process?
If they have companions, so some stars don't live on their own, they have like binary companions. So sometimes if a star explodes, it can interact with its nearby star, and we kind of see these things called, they're called runaway stars. So they're stars that move at like crazy velocities, like compared to everything else around them. And it's because these supernovae have kicked out the star, and so we can look for these high moving things and trace them back and try and figure out if they came from a supernova. So generally they get kicked out of the system. Yeah.
Thank you. Is it possible to study supernova remnants, or do they just sort of disappear off the?
Yeah, there's a lot of supernova remnants you can look at. I mean, the Crab Nebula has been visible for 1,000 years now. So
Yeah,
yeah.
but do they know what then happens to the remnant?
I mean, it will continue to expand and fade eventually, and like you can see, obviously you can't track one remnant through its whole life, but you can get a population of remnants and kind of say like, well, this one's older than this one, and then kind of make comparisons like that. Because some of them look kind of similar, so you can kind of assume they were similar kind of explosions. But yeah.
Oh, thank you. So how many do you think there are currently that are being studied? The remnants.
Actual remnants, probably a few hundred. I don't know. Yeah, hundreds. Yeah.
Hi, I was really struck by your size of the convection cell
Yeah.
in these supergiant stars. And is that a relationship that continues with even bigger stars, that the cells get bigger? And what does that mean for the sort of magnetic behavior of supergiants compared to the sun?
Yes, that's a good question. So most only stars up to around 30 solar masses will pass through this kind of like red supergiant phase, and they're very convective. Hotter stars have different processes going on the surface. It's also more difficult to kind of figure that out because you need to have UV data to understand them better. But the convection cells aren't driven by anything magnetic, so I don't think there's that many people working on the like magnetic kind of interaction of massive stars compared to a solar-like stars. I'm not actually sure about that.
Any more questions? All right, I have a question for you.
Yep.
You've got the shockwave from a supernova. It interacts with a distant molecular cloud.
Yep.
Is that going to trigger star formation eventually?
It can do, yes. Yeah, so it can cause loads of material to kind of compact, and you can kind of trigger new regions of star formation. So that's happening in young clusters all the time. So when they're really, really young and there's still a lot of material around, these supernova go off and they cause these dense regions that can trigger more star formation. Yeah.
Thank you.
Thank you so much, Dr. Beasor, for being with us and to help us celebrate 35 years of Hubble. I'm assuming is it still active? Has it decommissioned yet?
No, I literally applied for time on it last week.
Did you?
So I hope it's still going.
Have any idea of how much longer further in the future it might be of use?
They've said at least till 2026, 2027, but I don't know. It's still going pretty strong.
Incredible. Absolutely amazing. Thank you so much for being here. Let's give a round of applause. Thank you. Thank you. And if anyone's missed our library exhibit upstairs on the first floor, you are welcome to go visit our library. Thank you so much. Don't blame me.